Hi, I'm Caleb Parton.
And I'm Lily Lee. We're excited to share with you our work from the summer at Georgia Tech, mentored by Professor Dan Margulies. Thank you to the organizers for giving us a chance to share our work.
So the problem we're interested in is the polynomial recognition problem, which goes as follows. Given a map from the complex plane to itself, how do we detect whether it is a polynomial, and if so, which one? In general, this is a difficult question to answer, so we restrict our attention to topological polynomials up to Thurston equivalents. Two topological polynomials are Thurston equivalent if they are conjugate to each other by isotopic orientation-preserving homeomorphisms of the plane.
One celebrated problem in polynomial recognition is Hubbard's twisted rabbit problem, which seeks to characterize the image of the rabbit polynomial under powers of Dane twists around its ears, as shown in the picture. Work of Bartoldi-Nekrashevich gave the first solution in 2006, and more recently, Belklinier, Margulies-Winarski provided a topological perspective on recognizing polynomials. And one application of their work is a new topological solution to the twisted rabbit problem.
Key to the solutions of both Belklinier, Margulies-Winarski, and Bartoldi-Nekrashevich is a virtual endomorphism of pure mapping class group of the puncture plane. We treat topological polynomials as branch covers over C, and the homeomorphism of the puncture plane is said to be liftable if its lift through said branch cover restricts to a homeomorphism of the original plane. Since each puncture downstairs lifts to two preimages, the homeomorphism either fixes these 2 points or it swaps them. A liftable homeomorphism is one that either fixes all pairs of points or swaps all pairs of points, such as the one on the left. The map on the right side is an example of something that swaps some points and fixes others, so it's not liftable. Liftability is preserved under composition and isotopy, so we can define the liftable mapping class group, or LMod, as a subgroup of the pure mapping class group, PMod, that consists of liftable mapping classes.
Our first result is a classification of the virtual endomorphism taking all the liftable mapping classes to their lifts with respect to the rabbit polynomial. The short exact sequence we're displaying here describes that we can associate to each mapping class a bit string where the digits indicate whether a post-critical point is swapped with its twin in the lift. Two bit strings are equivalent if they're the same up to flipping all the bits, which accounts for one non-trivial deck transformation swapping all the points. So the map above is a homomorphism. On the left side, we see that the bit string associated is all 0, and on the right side, there are some zeros and ones. Now, the liftable mapping class group is the kernel of this map because it consists of mapping classes that fixes all pairs of points or swaps all pairs. Using this characterization, we can obtain a generating set for LMod and characterize the lifts of each generator. Now armed with a combing algorithm to turn any liftable element into a product of generators shown here, we now know how to lift any element of LMod.
It turns out that twisting a polynomial by a liftable mapping class is Thurston equivalent to twisting by the lift of that mapping class. In case the result of lifting is no longer liftable, we can instead perform lifting by borrowing, an analogous procedure for non-liftable mapping classes, which for the sake of time, we're not going to cover. To analyze twisting by a general mapping class, we ultimately seek a sequence of operations where we lift when we can, lift by borrow otherwise, so that the resulting mapping class is still Thurston equivalent to our initial one, but is now hopefully simple enough to identify. Our results give first steps to solving the twisted n-eared rabbit problem.
Another generalization is to relate twisting the n-eared rabbit and twisting the n+1-eared rabbit. Inspired by the Berman exact sequence, we regard a mapping class applied to the n+1-eared rabbit as having two components. One is a point push of the additional post-critical point, which is label number 2 in the picture, and a pure mapping class on the plane with one less puncture. The pure mapping class group of the n-punctured plane is a semi-direct product of the free group corresponding to the point pushes and the pure mapping class group on the plane with one fewer puncture. Our work proves that a mapping class is liftable if and only if its two components are liftable, as shown on the slide. And that's the end of our talk. Thank you so much for coming.
Thank you.